Hello, everybody. Here is your snow day work on series. This is so we can immediately start on something called Taylor series the next time I see you. In class, we didn't quite get to geometric series. We had just finished going over the video you tries, and I also had just given you this list of 4 series, both infinite and finite, and I asked you to write them using summation notation. So that meant pick a starting term, and I believe for all of these I said to start at 1 and then write the general term a sub n, and then either put infinity or the ending term. So if you didn't finish that in your notebook yet, can you pause now and finish this, and then I'll show you the answers. Here are the answers for the 4 U tries. So hopefully you got those okay. And I just want to emphasize again that you can really use any index letter here. I and N are the most common, but sometimes we'll see J as well. The important thing is that whatever you put here as your index starter is used here in your A sub N generator definition. Don't mix up different letters. It won't work. So we need to talk about arithmetic or geometric. Now, when you look at this word, you probably are thinking arithmetic, right? But whenever you're talking about sequences and series, you say arithmetic and then geometric. Now, an arithmetic series is a series such that, or a sequence, I guess, a difference of consecutive terms is constant. So the key here is the difference, and we call that difference letter D. So if I look at this infinite sequence here, you can see that to go from one term to the other, what we're doing is we're clearly adding 5 each single time. So that means our common difference D is 5 here. Let's contrast with the sequence we see here, and you can see that we're not adding or subtracting the same thing to go from term to term. What we're doing is we're actually multiplying by something constant. And what we're multiplying by is 1/5 to go from term to term. And if you multiply by something each time to go from one term to the other, that is a geometric sequence or series. Our common ratio R here, so R is for ratio. The common ratio here is 1/5. So instead of the difference of consecutive terms being constant, we have a ratio of consecutive terms being constant. Now let's think about what these would look like when they're graphed, because that's very important in understanding why we prefer one over the other, because we only care about one of these. So let's figure out which one we're going to care about. So if I took this and I graphed, our first term is -4. Our second term is 1. Our next term is 6. Our next term is 11, etc. You can keep going. This follows a linear pattern. And a linear pattern never levels off at anything. It goes up or down forever. You could have an increasing line or a decreasing line. The point is there is no leveling off. And that's bad here. No leveling off. Because whenever we do series, all we care about is that things eventually level off. Or we have a fancy word for that, converging. If something doesn't converge, we don't care about it. So the one that we're actually going to care about is the geometric, and let's take a look at why. If I go and I graph the terms that I had here, 25, 5, 1, 1/5, and 1/25, you should recognize this as an exponential decay function. And exponential functions, whether they're growth or decay, they always have a horizontal asymptote. And decay is better. You can see these terms are decreasing, and the individual values themselves, like 25, 5, 1, 1/5, they are converging to, and you want to think, what do the y values get really, really close to? They're clearly leveling off at 0, and that's because the horizontal asymptote is 0. For our notes here, a geometric sequence or series is going to look exponential. Now, right now, what I wrote here is a sequence. It's just a list of numbers following a rule. If I were to actually add these up, then I would have a series, as you already know. And when I add these up, something special could happen to a geometric series. We're going to talk about that in just a few minutes. So for decay, the values can converge. I don't want growth, because think about growth. Exponential growth just keeps going and going and going. There's no leveling off. I don't care about that. I care about the decay. There's clearly leveling off, and it could totally converge, which we're going to be interested in. So let's take a look at this list right here. And what I want you to do is just write these down and decide, are they geometric or not? And if they are geometric, what is R? So just pause, take a moment and do that. All right, so here we have a geometric series. It's going down as a decrease, so it's decay. And to go from one term to the other, we multiply by 1/3. This is definitely not linear, so it's not arithmetic. It's not geometric either because we don't multiply by the same thing each time. I multiply by 2, then by 3, then by 4, then by 5. Definitely not geometric. Here we have an alternating, the sign is changing, an alternating geometric sequence, and the common ratio is -2. Now, one rule you're going to need to know here, first of all, let's think back to Algebra 2 here. Whenever you had an exponential function, and make sure you write this down, exponential function, whenever you did Algebra 2, you learned that an exponential function can be written as y equals a times b to the x, where a is the first term, the y-intercept, the starting value, and b was your base, and it was your growth or decay factor. And that was whatever you multiplied by each time. So if the base was 2, it means you multiplied by 2 to go from term to term, etc. Now there's another rule that you're going to need to know whenever we do geometric series and sequences, and that is if you have a geometric sequence and you have a first term a sub 1, we'll always call it a sub 1, common ratio r, you can get the nth term by doing this. A sub 1, you take your first term times, raise your ratio to the n minus 1 power. So if you want the 20th term, take your first term and do the common ratio to the 19th power, for example. So this is something you're going to need to know whenever we do series in general. And another formula you're going to need to know is if you are trying to take a finite geometric series. So let's say we have like 5 plus 1/5 plus 1/25, and we just stop right there. We'll put 25 in. This is finite because I'm stopping right here, and I want to add these up. You could, of course, just go in your calculator and type these up, but what if you have something written in summation notation like that? Or what if you have 100 terms? You don't want to type 100 things in your calculator. There's a much easier formula. The sum of the first n terms of a series is going to be a sub 1, 1 minus r to the n over 1 minus r. So if you want to sum up the whole thing, you just take however many terms there are and make that n. So we'll talk about what exactly that s sub n is in just a moment here. So let's take a couple examples here. Let's take a look at the sum. I equals 1 to, let's do 16, 4, 3 to the I minus 1. Okay, so you might look at this and think, all right, this is my generator a sub n. It's definitely finite because I stop at 16, and compare this to this. You know that your starting term a is 4. You know that your base or ratio here is 3. So the terms differ by a constant of 3, constant ratio of 3. Let's actually get a few terms out. Sometimes when you look at a generator, it's hard to tell exactly what's going on unless you actually expand it and plug a few I values in. So let's start with I equals 1. 1 minus 1 is 0. Anything to the 0 power is 1. We have 4. Plus, plug in 2. 2 minus 1 is 1. 3 to the 1 is 3. Times 4 is 12. Let's get one more. 3. So 3 minus 1 is 2. 3 squared is 9. 9 times 4 is 36. Plus dot, dot, dot. And then it stops whenever we have 16. I'm not going to do 16 right now. So anyway, if I plug into this formula right here, what I can get is the sum of all of these numbers added up from 1 to 16 in terms of the place. So I'm going to do a sub 1, which is the first term, which is 4. Then I do 1 minus my common ratio to the 16th power. No idea what just happened there. All over 1 minus my common ratio. All right, so if you go on your calculator and you do 3 to the 16th, 1 minus that, divided by 1 minus 3 times 4, you would get this very large number of 86,000 or 86,093,440. Let's do one more example for a finite geometric series. Let's take this one here, and remember a times b to the x. So my first term, a sub 1, is clearly 6. Now let's say you didn't know the rule that this term will always be your starting term. What you could do is you could take your starting index 1, plug it in, and you would get 6 times -2 to the 1 minus 1. That would be -2 to the 0, which is 1 times 6 is 6. So you can just take this outside term, or you could actually plug in your starting index and get the first term. Now my common ratio is -2 here. This will be an alternating series because we have a sign changer of -2. Okay, so let's plug in. I have a sub 1, which is 6, times quantity 1 minus my common ratio. Now I want to do the whole sum here, which goes up to the 8th term. So that means S sub 8. So I'm going to go to the 8th all over 1 minus R, so 1 minus -2. We can plug that into a calculator. You'll get a sum of -510. So it's very easy to sum up a finite geometric series because there's a clear ending value. It doesn't go on forever. But the real question is it possible to add up an infinite geometric series and get a finite sum? Now I want you to think about this here. Is it possible to add up an infinite amount of numbers that go on forever and get a single value? It seems impossible, right? Because shouldn't the number keep getting bigger and bigger and not be a finite sum? But let's take a look at this infinite series. Now the common ratio is clearly 1/2. It is decreasing. And you can see that the individual terms are getting smaller and smaller, probably towards 0. In fact, it is towards 0. And what we want to do is try adding up what are called partial sums. So a partial sum is the sum of the first n terms of an infinite series, and the partial sum can approach a limiting value. So for example, let me find some partial sums here. S sub 1 is the partial sum of the first 1 term, so 1/2. S sub 2 is the partial sum of the first 2 terms. 1/2 plus 1/4 is 0.75. Let's do decimals because it's easier to see what's actually going on here. S sub 3 is the partial sum of the first 3 terms. For example, when you add those up, 0.88. So as you can see, whatever your partial sum is, the 5th partial sum, that's your subscript, and that's how many individual terms you add up. And also notice that your partial sums go from 1/2 to here, to here, to here. They're clearly approaching a value, and the value that they seem to be approaching is 1. So the terms themselves seem to be approaching, so let's take a look here. The individual terms are getting smaller and smaller and smaller. So the individual terms appear to be approaching 0, but the sum or the partial sum S sub n appears to be approaching 1. It's important you don't mix those two things up. Another thing is let's try actually plotting our partial sum so we can see something here. The visual here is that the individual terms go from 1/2 to 0.97, and they're definitely leveling off, or they appear to be leveling off at 1, which would be a horizontal asymptote. So you know what, let's go ahead and try plugging into a formula to see if we can get something. Let's take our formula right here for a geometric finite series and plug in our information and see if we can find anything out. My first term was 1/2. My common ratio R was 1/2. Now let's go ahead and simplify this. I have 1/2 here, 1 minus 1/2 to the n, and then 1 minus 1/2 is 1/2 in the denominator. Well, those cancel, so what I'm really left with is 1 minus 1/2 to the n. So S sub n equals 1 minus 1/2 to the n. And if n approaches infinity, 1 minus 1/2 to the infinity approaches 0. So I'm really just left with 1. So the partial sum, the limit of the partial sums is 1. Now let me give you an actual formula. So now that we know it's possible to sum an infinite geometric series, we need a formula to find that sum. So the general sum of an infinite geometric series is the first term a sub 1 over 1 minus r. It's important to note that this formula only works if the common ratio r is less than 1. Because if your common ratio r is greater than 1, you have exponential growth, which is never going to level off. What I want you to do is to take this formula here and apply it to these 3 sums, infinite geometric series. Find the sum if possible. If not possible, state why it's not possible. So you're going to pause the video and you're going to do that. The last comments I have for you are down here. Write this in your notes, and since I'm basically out of time, I might have just enough time to write this. Make sure you go back and you actually find those sums here. The sum of an infinite geometric series is going to be the limit of the partial sums S sub n. A general infinite series is written as n equals 1 to the infinity a sub n. Now we'll finish this in class. I don't want to rush too much, but enjoy the rest of your snow day. I'll see you tomorrow.